Good morning, this is Ben. We're going to do a little bit more Lenz's Law. So after this, we'll be moving on to some other concepts. But Lenz's Law is just such a big part of the AP exam. And this is really like the last section. So with the AP exam, you have 3 free response questions. And there's a good chance that the third question you'll have on the free response will be Lenz's Law. They tend to go in order. So this will be the last major topic that we cover for AP Physics. But after this, I'll go over the idea behind DC motors, generators, AC current, using capacitors and inductors as filters, and transformers and that kind of thing. That's actually a huge topic, but I'm just going to briefly go over the ideas of them because you already have all the basic fundamental knowledge, and I think even though they won't be on the AP exam, going over how they work will help reinforce the knowledge you already have. So that's why, even though they're not in the test, I think touching on transformers, AC, etc., might be kind of nice. Okay, so on to Lenz's Law. Here's a problem. Whoop, got a wire, got another wire, got the same wires, but from a different view. So the figures above represent different views of 2 long, straight horizontal wires. Okay? And here, when they say long, they mean you can assume infinite. And that gives you the B equals mu naught I over 2 pi r for the magnetic field due to an infinite wire. Horizontal wires 1 and 2, carrying current I and I2, where I2 is 2I1. Okay? Respectively in directions as shown. The wires are held in place. Okay, so basically the idea is there's going to be forces between the wires because they both produce magnetic fields, and the magnetic fields would interact. It's saying that one wire doesn't fly off, changing the situation. Hold in place. In figure 1, the current is directed out of the page. Yep, that's normal convention. And wire 1 is a distance d above wire 2. Okay. Point P is a horizontal distance d from wire. Yep. Now that d looks different. Is that bigger? Doesn't matter. Not drawn to scale. From above wire 2, express your answers to part A and B in terms of I, D, and physical constants as appropriate. Use Amperes Law. To derive an expression for the magnitude of the magnetic field at point P to the wire. Okay, so clean up the board. So what we're going to derive is this right here. But they're saying, well, don't just write down the formula. Use Amperes Law. And we want to find the magnetic field at P. Use Amperes Law to derive an expression for the magnitude of the magnetic field at P due to wire 1. So we're looking at just wire 1 at this point here. So first off, we're going to use the right hand rule to kind of figure out where we're going here. So thumb along the direction of the current flow, which is out of the board, hands wrap around, and we're going to get a magnetic field that's circular, and specifically at this point it's going to be upward. There we go. Okay, and we're supposed to use Amperes Law, and we are given Amperes Law, I think, in our formula sheet. So right here, right this right there. Eesh, that's a terrible highlighting. This right here, that's Amperes Law. B dot dl equals mu naught I, mu naught times I. Okay. So let's go back to our infinite board. So I think we actually did this earlier. Well, at least the same. It's how you do it for an infinite line. So this is what? B dot dl integrated over a closed loop equals mu naught I. Check real quick just to make sure I'm kind of close. Closed loop, B dot dl, mu naught I. Okay? And I'll put in the vectors. So these are vectors, and that is a dot product. So let's see here. Start by looking at this and thinking, all right, so it's a dot product. Direction of B is straight up, and the direction of this circle that we're integrating over. Ooh, very convenient. No, don't put a v in the middle. Start cooperating more. There we go. Like so. Ooh, oh, at least it was the right size. I feel bad when yelling at something actually works. I'm like, oh, did I emotionally scar it? I don't know. Okay. So L will be in the up direction. Small section of L right here at this point will be upward because it's the length of the circle. So a small piece of the L, dl, will be up. The magnetic field at that point will also be up. And as it goes around the circle, the magnetic field and the small unit of length will be in the same direction. And so the theta between the two will equal 0. Dot product is cosine of theta. I remember that because it would make sense if the cross product was cosine, because they both start with C, but they don't. Therefore, the cosine is associated with the dot product. I know, just a mnemonic, don't overthink it. Cross product is actually sine. Okay, so they're both in the same direction. And we have b dot dl, so that equals b times dl, which is b is a constant. dl equals mu naught I. Well, this portion right there is just the circumference. And so when we move it over, we got mu naught I over 2 pi r. And let's look back to see what kind of units they want us in. Driving accretion magnitude at point P due to wire 1. Okay, so we know point P is at distance D, and we know that I1 is just I. So then this will be mu naught I, I over 2 pi D. Okay, perfect. I'm going to erase this then, because it has served its purpose. It sounds really harsh. Really harsh. You've served your purpose. Time for to be erased from existence. That is harsh. I feel bad now. Maybe it's saved somewhere in the computer cache. I don't know. Is the cache like the equivalent of heaven for electrons? I don't know. Much deeper than I expected to go. Okay. Now I got distracted. Derive an expression for the magnitude of the net magnetic field at point P. Derive an expression for the mag. Okay, so now they're like wire 1 and wire 2. Derive an expression for the magnitude of the net magnetic field. Okay. We got this. Go team. So I'm going to take this, clean it up. Now I have second thoughts every time I erase something. Not like I have second thoughts when I eat a hamburger. But I should, though, because like, oh, that poor cow. Shed a tear. So delicious. I honestly believe that vegetarians have the moral high ground. I've just accepted that. Like, it's delicious. I'm a terrible person. Truly terrible. Okay. So then we do the same thing with this. Do the thumb. Okay. So we got a triangle where B1 is going up and B2 is going into the board. And so I'm going to redraw this triangle like this. So this is B2, this is B1. It's kind of like we rotated it. I could probably draw it on this. Nah, it's okay. Okay, so then one expression for it. So we got mu naught I plus 2 pi D. So we're going to have something like, we're going to have to do the Pythagorean Theorem. So B net squared equals B1 squared plus B2 squared, which is mu naught over 2 pi D times, let's see, we got 1 squared plus, I'll do it this way, I squared plus 2I squared, which equals mu naught I over 2 pi d. And this is all actually supposed to be squared as well. Times 5. And I guess this portion here is squared. Man, I am not making this simple. Long story short, the ending that you probably already saw, square root of 5. Mu naught I 2 pi d. So what happened here was we have a triangle, we have 2, we have 1, the hypotenuse is square root of 5. And then all these others, the mu naught I 2 pi d, well, those, they were squared, but then they were all square rooted. It's a wash. So the net, B net, since these two vectors are perpendicular to each other, we find the distance, the sum of the two vectors using the Pythagorean theorem. That was not clearly explained, but it's not that tough a concept. I'm pretty sure you got it, despite my bumbling. So I will redo that as, what? Oh, don't, arg. Green. B net magnitude equals B1 squared, B1 plus B2 magnitudes, which equals square root of 5 mu naught I over 2 pi d. There we go. Drive an expression, calculate the numerical value of the angle to the horizontal for the direction of the magnetic field at point P. Okay, so magnetic field looks kind of like this. So we have B1 is going up, but B2 is along the horizontal. So when I draw the triangle, it's going to look like this. And there's going to be a mu naught I 2 pi d involved, but it's going to be with both sides. So I am going to simplify this to 2 and 1, because B2 will be twice B1. We're looking for theta, so using our SOHCAHTOA, we can say that tangent of theta equals, that's a terrible tangent theta. I can do better. There we go. Equals opposite over adjacent, right there, which equals 1/2. Therefore, theta equals arctan. Some people use tangent with a little -1 symbol. I don't, just because that's, for me, it's easy to get confused of 1 over tangent. So that's why I use the funny arctangent, arcsine, arccosine notation. Okay, so calculate the numerical value of the angle to the horizontal for the direction of the net magnetic field at point P. Okay, and this is going to be calculator, or in my case, Wolfram. I love Wolfram. Okay, arctan of 1/2. And it'll probably give us this in radians, which I don't care. But I want a, ooh, yes. No, that's radians. 26.57 degrees. It's easier for me to visualize. I have more of an intuitive feel for degrees than I do in radians. I don't know if it's because I grew up with them, or if it's just because, yeah, it just feels, they have the right number of divisions where it'd be like, wow, pi over 2. It's like, I don't know what that means. Kind of like degrees in Fahrenheit and Celsius. It's like, well, Celsius is just, 2 Fahrenheits. It's like, not really. Then you have to add 32. Okay. Hoop, hoop. Put this guy here. Draw an arrow to make it feel like I'm doing what I'm supposed to. Here we go. Wire 1 is now released. Which of the following best describes the initial motion, okay, initial, due to the magnetic field of wire 2, assuming gravitational effects are negligible? Okay, so maybe we can get rid of all this. So for this, I'm going to use force equals Q times E plus QV cross B. We're assuming no electrical fields, so 0. And I'm going to look at this one first. So we have this wire going this way. So V cross B. So B in this case would be into the board. So we're looking from the effect of wire 2 on wire 1. So the magnetic field created at wire 1 is into the board. Yeah, it's hard to see, my circle is too small. Into the board. And therefore the theta between the two, theta would equal 0. Sine of 0 equals 0. Therefore, there's, from this view, there's no magnetic force really on wire 1. Okay? Now if we look at this one, so we have wire 2 here. Magnetic field goes like this. So here we'd have magnetic field coming out of the board. This way over here, we'd have magnetic field going into the board. And before, on the previous one, we looked at magnetic field right here. I think right there. No, right there. And so for this, we would have, we have current going this direction. So V cross B would be V cross B. Is that true? Maybe that's true. So V cross B. So we get a force going this direction. And then on the up front, we have V. No, it's backwards. Totally backwards. Why did nobody stop me? So V cross B. Force going this direction. Out of the board. And then for this one, it would be V cross B going this direction. Yep. And when you see this sort of opposite directions of the forces with an axis in the middle, there's basically an axis. You're going to get a torque, you're going to get a rotation. So you're going to get a rotation going clockwise. So now the thing is, I wonder about the force. So all these forces are going to cancel each other out. So these forces, I think they're going to get smaller as they go further up, because you have this mu naught I over 2 pi r for the magnetic field due to a line. And as the r gets bigger, and this is due to wire 2, the forces will keep getting smaller, but they'll cancel each other out, and they'll be symmetrical about wire 2. But you'll have a positive torque in the clockwise direction. And so So they're saying, which of the following best describes? Which means there's only going to be one answer here. We'll rotate clockwise in figure 2. Yep, and we'll not move in figure 1. Yep. And that's because we have the torque. And the justification I would have would be, I'd say something like, well, forces cancel, torques exist in figure 2. And then I would draw the forces here, this force and that force, and be like, oh, okay, torque. And I might write this, torque equals R cross F. maybe. If you have time and you feel like it. But you don't want to write wrong things. I'd leave that off. Leaving that off's better because you'd risk writing something that's incorrect. Though that is correct. You don't want to... Yeah. I just draw the forces on the picture. Okay. Go to this guy. Whoop. Bring in the new one. Center it just so it looks pretty. Zoom in appropriately. Okay. Wire 1 is now replaced by conducting rectangle loop of length L. Okay. Width W. Also okay. And resistance R. Okay. I will draw in a little resistor. Hop, 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 hop. R. The loop is placed a distance D from wire 2 as shown. The loop, wire, and distance D are all on the plane of the page. The loop side of the loop, long side of the loop, is parallel to the wire. Current I2 for wire 2 is decreasing linearly as a function of T. This is a really long question. For 15 minutes, you're going to have to move quick. I sympathize with your plight. It means I understand it. I don't feel your pain. That'd be empathy. Time t according to equation I2. Okay, where k is positive energy, units each of the following given expression for the flux as a function of t. Okay, so almost since this is so long of a question and you kind of intuitively be like, okay, this is what it is, you might want to go for it. But I'm going to show you kind of where this comes from. So we're looking for flux. So flux equals B times A, which equals B times length times width. But B changes over that length times width. So it'd be more like B times... actually, it'd probably be more like delta L, delta W, and then you do a double integral. But we know that the length is constant, so this will be B dot times L times dW. We're integrating from D to D plus W. So if you look at this as a double integral, then when you integrate for L, you just get a constant. I don't know if you've experienced double integrals yet. You should. They should teach double integrals in second semester calculus. I know, me wishing that right now, not very helpful to you. So, you're probably looking at this sideways and wondering what's going on. There we go. Slightly better. So, we know that L is constant, the length from left to right. B will change because it's mu naught I over 2 pi r. And then that R is basically W. So we're going to have to rewrite this one more time. Mu naught I 2 over 2 pi W dW integral d to d plus w. And they looks like they use r here. So instead of having w here, I'll call this r. Okay. So now let's take a look at these guys and see which one is correct. So it makes sense that we're going to integrate from d to d plus w. So we got this one's okay, that one's okay, that one's wrong, that one's wrong. And then here they have an R in the bottom, and they don't have an R in the bottom there. And this R in the bottom comes from the magnetic field due to the wire. So this is going to be correct answer. And you could probably just, without going through all the details here, you could probably just look at the differences and be like, okay, it makes sense I'll do from D to D plus W. That's just an integration thing. Yeah. Yeah, you'd almost be better off just guessing which one it was. Again, it's going to depend on how much time you have. If you have enough time, go through the derivation of such, but you probably won't. And so if you can be like, all right, this is the one that seems obviously correct, it'll save you a little bit of time. This is almost like two complete problems shoved into one. And they're trying to give you a break by not having you actually just write this out yourself. But my trust in where the test is trying to lead me is minimal. Okay, given that the flux through the rectangular loop as a function of time is given by the equation, yep. And here you can tell, all right, natural log, and what's happening is everything here is constant except for the r. You take the, ooh, did I forget the L? I probably forgot the L there. Whoop. Everything here is constant except for the r. When you take the integral of 1 over r, you're going to get natural log. And then right here, this is telling you, okay, that's the top integration, that's the bottom. Drive an expression for the magnitude of the current, if any, induced in the loop. Given that the flux through... Okay. So what they're saying is current. Current. So current equals V over R, or voltage over resistance. In this case, it's going to be induced electromotive force, which is negative d flux dt over R. We know that flux is this, and it's going to be derivative with respect to time, which is only that portion right there. So everything else is a constant. So if I zoom out just enough, then we can see that it's mu naught IL over pi times natural log of d plus w over d. And then we're going to multiply by negative k. But then there's also a negative over here. But since we're looking for the magnitude, the signs don't matter. And that's the answer. So all I did was I took the derivative. I pulled everything out because it was a constant, except for this portion right there. Did I forget the L again? That L, nope, I didn't. Okay. For this portion right here. That portion is all we're concerned about because everything else is constant. I know I tend to abuse constants, but who cares? They're constants. And so that the 1 disappears because constant, but we get to keep the k because it's tied to a variable t, which we are differentiating by. Okay, what is the direction of the current, if any, induced in the loop as seen in figure 3? Okay, induced current. Okay, so the way, what is the direction? This second part is actually quick if you follow their prompts, but I could see how you get easily bogged down in this. So we know that magnetic field of a line equals mu naught I over 2 pi r. We also know that current is going down. Therefore, magnetic field original is going down through the loop. Therefore, the flux original within this loop is also going to go down. Therefore, the flux induced will rise. Therefore, the magnetic field will rise in the same direction that it's already in. It'll still be induced. Therefore, the current will be, okay, so magnetic field is into the board. That was my thumb going along the wire, direction of current, and then fingers going in the direction of the magnetic field. So this is saying is the original current is dropping. That's how we got the negative 1 minus kT. Therefore, the magnetic field due to the wire is dropping. Therefore, the flux within this rectangle is dropping. That will create a flux induced that goes up, which will be created by a magnetic field that's rising, which will create a current in the clockwise direction. It needs to be this direction. So clockwise will be the direction of the induced current. Clockwise. And the idea there is, then comes back from Lenz's law, where there is an induced voltage, which creates an induced current that opposes the change in flux. And that whole opposed change in flux is this portion of the justification right there. This induced flux arrow will always point the opposite direction of the original flux change arrow. And for justify your answers, I would just do that. Arrow analysis. Okay? Are you guys up for one more Lenz's law problem? Yes, of course you are. Well, and for now, you probably just turn the video off. Not like I can really Nope, yes you are. Because you want to pass the AP exam. Well, just not fail it terribly. Though I am confident you guys could pass it with minimal preparation. It's kind of hard to decide how much preparation you should do for these exams, because chances are this is not the only AP exam you'd be taking. You're probably also taking English and a history, maybe like a psychology or some other one too. And some of them are pretty easy, and you want to balance. It's the sort of thing where you don't want to crush any one exam. You just want to barely pass every single one of them. So, which is, would be ideal, I guess. But then it's risky to just kind of barely pass, because you kind of got that normal curve distribution of how you actually perform. It's a risky game. There should be some sort of an accounting. Interesting. I wonder if there's a way to calculate these things. That might be an interesting business endeavor. To be the guy that you take a small pretest and they're like, all right, you should study for 6 hours more on these topics. I could put some actuarial skills to use. That'd be nice. Okay. Circular wire loop with because then you could do insurance, AP exam insurance. That'd be interesting. That would be interesting. So you have an AP test studying thing, and then you offer some sort of insurance. It might be in the form of using money would be too complicated just because of the logistics and the tax implications. But and then money laundering, know your customer, KYC. I don't know. There's something there. It's gonna be exciting. Ooh, maybe you could use cryptocurrency. Worry about the transaction cost of those. Couldn't be Bitcoin. Okay. Circular wire loop with I could do an initial coin offering. Too tangential at this point. A circular wire loop with radius 0.1 meters. Okay, so they're giving us radius here, not area. And it's specifically not diameter. And resistance of 50 ohms. Okay, it's held in place. Okay, it doesn't move. Horizontally in magnetic field B. Directed upward at an angle of 60 degrees. Not perpendicular. And you can see here it's 60 degrees from the vertical, not the horizontal. As shown in the figure above, magnetic field in the direction shown is given as a function of T by magnetic field of T equals that. But then they give us the numbers. So I'm just going to write B of T equals 1 minus T over 5. Yes. Derive an expression for the magnetic flux through the loop as a function of T. Okay. So magnetic flux equals magnetic field times area dot area. There we go. And this is what? Is it cosine? I think it's cosine. Yep. Because cosine should be cross product, but it's not. So cosine goes with dot product. There we go. So we'd have 4 times 1 minus T over 5 times cosine of 60 times the area, which is pi r squared, where we know that r is 0.1, which is 1/10. So, and then cosine of 60 is the same as sine over 30. Cosine of theta equals sine of 90 minus theta. And that's how you can convert between cosine and sine. And I always do sine because I have thumb rules, which I know for sine. You should not actually use these in real life. Well, no, you should use them in real life. You shouldn't use them on tests, especially when you have a calculator. So basically, if you're less than 42 degrees, then you just divide by 60. If it's between 42 and 75, then you do theta plus 25 divided by 100. And if you're greater than 75, then you're like, probably 1. And so the sine of 30 is 30 divided by 60, which is 1/2. That's the only one that's actually exact. Well, I guess 0. But the others are within like 5%. Okay, so we have, let's see here, 4 divided by 2, because that's the 1/2 there, times 1 minus t over 5 times pi over 100. 100 is 0.1 squared. So this is, let's say, 4 over 200, which is 1 over 50. One minus t over 5 times pi. There we go. And looks good. Drive an expression. Make sure we got everything. Function of time. Yep, only a function of time. Okay. Calculate the numerical value of the induced EMF in the loop. Okay, so this is flux. So we want the EMF. So induced magnetic force is negative d flux dt, which equals, so this is a function of t, pi over 50 is a constant, and we'll do times negative t over 5. Put the negative there, and we have pi times t over 250. Calculate the numerical value of induced EMF in the loop. Oh, gosh darn dang it. This t disappears. So we take the derivative of, you take the derivative of this, the 1 disappears, and then the derivative of negative t over 5 is just negative 1/5. And so we have pi over 250, which is why they don't give us a specific time t to calculate it. If they did, I totally would have fell for that trap. Human performance trap. So pi over 250, it's like 3 over 250. Let's do 3.1415 divided by 250, and we get 12.6 millivolts, 12.6. So we have 12.6 millivolts, where milli is just 10 to the negative third. I should probably underline that so I don't lose it. There we go. And calculate the numerical value of the induced EMF and the loop. Yes, I'm good with that. Calculate the numerical value of the induced current in the loop. Easy. So I equals V over R, which equals epsilon over R, which equals 12.6 millivolts over 50. So we have 1, 2, 3, 4, 5, 6 times 10 to the negative 6, and we get 251 microamps equals 251 microamps. Yep. 251 microamps. Okay. Calculate the numerical value in the loop. Check. Okay. What is the direction of the induced current in the loop as viewed from point P? Ooh. This sounds kind of challenging because, okay. So I'm going to draw the loop like this. Actually, I should probably clean my board up. Yes. So the loop is like this, and the magnetic fields are going this way. So when we turn it like this, as viewed from point P, then we have the magnetic field. I'm going to say it's coming towards us. It's not really coming towards us because it's kind of going off at a funny angle. But we kind of have to. It's the best. If I drew all those crazy lines, the only part that's going to matter for flux. So the idea with a dot product is you are projecting this vector down here. And so we can decompose this vector B into a part that's parallel with the loop and part that's perpendicular to the loop. And then we just ignore this portion. So I'm just going to draw the part of the magnetic field that's coming straight at us. Okay, and we know that the magnetic field is lowering. So I'm going to say that magnetic field, original, is lowering. Therefore, the flux, original, is also lowering. Therefore, the flux induced will rise. Therefore, magnetic field induced rises. Therefore, the current, and so it's going to rise in the same direction. So we know the direction, then it's basically going to reinforce the field. So we know the direction is coming out towards us. And so you put your thumb along the direction of the magnetic field and then find the current of the loop. So if current is this direction, then you wrap your fingers along the direction of the current and your thumb points the direction of the magnetic field. And so we're going to have a counterclockwise. Except that second arrow looks dumb. There we go. Counterclockwise current coming around the loop. And assuming the loop is staying in the, no, up here. What is the direction of the current as viewed from point P? Counterclockwise. And this is the did I say justify your answer? This is the justification I would use. Right there. Assuming the loop stays in its current position. It's almost confusing because current and current. Present would probably be, never mind, not important. Calculate the energy dissipated in the loop in 4 seconds. Okay. So we know what the current is, and we have a constant induced EMF because the derivative of the magnetic field with respect to time is constant, and the EMF is the negative d flux dt. Therefore, the derivative of magnetic field being constant, the area being constant, we're going to have a constant EMF, which gives us a constant current, which means that it should be pretty easy to calculate. So energy equals integral P dt, where this is power. One way you can think of that is power is joules per second. I think it's measured in watts. Joules per second. So when you integrate with respect to time, you just get joules. So we're going to integrate from 0 to 4 of the power, which would be I squared r. You could also do use v squared over r. I'm going to use I squared r, which is 251 times 10 to the negative 6. This is going to be not very many joules. Times 50. Yep, 50. And then when we integrate this, we'll just get t. It'll be t evaluated from 0 to 4, which will then just be 4. So this will be 200 times 251 squared times 10 to the negative 12th. There we go. Yep. Yes. Okay. See if I can remember this. Quick memory. So if I do this number squared, and I lost it. Could have just done it. Alright, so that's this number right here squared times 50 times 4, so times 200. Times 200. And we get something crazy small. 1, 2, 3, 4, 5, 6. Times 10 to the 6th. And this gives us 12.6 microjoules. Equals 12.6 microjoules. Hop. Double, triple underline. Indicate whether the magnetic force and net magnetic torque in the loop are 0 or non-zero while the loop is in the magnetic field. Okay, so it feels like there's going to be a torque because magnetic fields want to align. So what's probably going to happen is there's going to be a current. It's going to create a magnetic field going up, and this magnetic field going up is going to want to align itself with this magnetic field. So let's look at it. We're going to look at this picture up here. And we're going to use our old friend, our reliable equation. Force equals QE plus QV cross B. We're going to assume the electric field is 0. And we're going to look at these portions right here. So we determine that looking from point P up here, the current is going counterclockwise based on this picture, which hopefully we did correctly. Otherwise, we're going to have trouble. And so when we turn it back over, we know that the current at the left side is going to be coming towards us. This is current. And it's going to be going away from us over here. So make sure that we got the spatial reasoning again right. Yeah, that seems reasonable enough. And we probably got 50-50 chance anyway, right? As long as we make an even number of mistakes, we'll probably be okay. Okay, so Q is assumed to be positive because current is positive charges moving in the positive direction. So Q is V, and we're going to I'm not going to assume that the magnetic field is straight up. I'm going to actually use the magnetic field given to us, like this. So we're going to have V cross B. Yep. So it'll be up and to the left. So we'll have a force going in this direction. And then the other one will be V cross B. So it'll be going this direction. And there'll be 90-degree angles right there. So, it's going to be exactly what I said, where it's going to try to align itself with the magnetic field. So these forces, when you add them together, will all cancel each other out. So there will be net magnetic force, 0. But there will be a torque, net magnetic torque, because you'll see that this is torquing the loop to be in line with the magnetic field, non-zero. And then justify both answers, I would just draw this picture. I'd write F force equals QE plus QV cross B, electric field is 0. And then I would draw the force lines, the current lines, the magnetic field lines, and that would justify where you're getting your answer from. Nice. So this is kind of the flow you're going to see with Lenz's laws type problems. Next time we'll go over some of the ideas behind transformers, generators, and just AC current in general. We really haven't talked about AC current. We've kind of sort of talking about it by seeing a varying DC current. So if you take a DC current and it drops off or builds up, it's like, well, that's kind of alternating current. But we really haven't seen it in talked about it as like, well, if it's periodic and it happens continuous. And AC current is such a big part of like normal life that it really feels unfair that it's just kind of like, yep, and then this is life. And it's like, but what about all these things we actually use? And so we'll cover some basic ideas behind AC current just so it cements the ideas you already have built in that you've learned for DC current, how they apply to the real world and specifically alternating current. So I appreciate you coming by. I will see you next time.